friends to this NPTEL online certification course of environmental soil chemistry, and today we are going to start week 7 of lectures or module 7 of lectures. And in this week 7 we are going to talk about the redox chemistry of soil, which is very important as far as the soil environmental soil chemistry is concerned. Now we will be discussing different aspects of redox chemistry, which is basically pertinent to the different soil processes. So, these concepts will be broadly covered. One is oxidation reduction reactions and potentials, and then we will be talking about EH versus pH and PE versus pH relations, and then we will be talking about measurement and use of redox potentials, and then we will be talking about submerged soils, which is very important, and then we will be talking about redox reactions involved in organic and organic pollutants. Now, remember these redox reactions are basically the short form of reduction oxidation reactions. So, these redox reactions are very much important for governing several processes in the soil depending on aerobic and anaerobic systems, depending on the presence of water, and also it can govern the movement and dynamics of several nutrients from the point of view of plant nutrition, and also it can control the fate of different nutrients as well as other materials which are present in the soil. So, that is why it is very much important to discuss the redox chemistry of soil. Submerged soil is a very important aspect of important aspect where we can apply these redox reaction more in more efficient way, because in the submerged soil which is submerged under water, these redox reactions can govern the conversion of different forms of nutrients depending on the oxygen presence or absence of oxygen rather. So, let us start with the first definition of oxidation and reduction. So, what is oxidation and what is reduction? Now, soil chemical reaction basically it shows the combination of proton and electron transfers, and oxidation we call it oxidation when there is a loss of electrons in the transfer processes. In contrast, in case of reduction there is a gain of electron. It is a common knowledge of chemistry. Now, oxidized component of or oxidant is the electron acceptor in case of oxidation, and in case of reduction the reduced component or reductant is the electron donor. So, in case of oxidation there is a loss of electrons, in case of reduction there is a gain of electrons. In case of oxidation the oxidized component or the oxidant is the electron acceptor, whereas in case of reduction the reduced component or reductant is the electron donor. So, the oxidant must be in close contact with the reductant in soil solution to govern these redox reactions. So, obviously, you will see specifically when we will talk about different reactions and different conversion of different elements, specifically in submerged soil, we will see that different oxidized form are in close contact with different reduced form. So, that there is dynamic changes of their dynamic change of the species occurs. So, this basically shows the gist of what is oxidation and reduction. So, here you can see this is a reducing agent which is A, and B is an oxidizing agent. So, B basically oxidize the reducing agent, and reducing agent basically reduce the oxidizing agent. So, you can see here these reducing agent which has excess of electron, they can give this excess of electron to this oxidizing agent, and by removing those excess of electrons it can be oxidized, and in other way these oxidizing agents which are having less amount of electron, they will gather or they will accept these electrons to be reduced to and then converted to into the reduced form. So, that is B. So, reduction is basically denoted by this blue line, which is component B, where it is gaining electrons. However, oxidation is denoted by these red lines, where it is basically loses the electrons. So, this is why we said that there has to be a close contact between the oxidized agent as well as the reduced agent for governing this redox reaction, specifically also in soils. So, what is redox potential? Now, redox potential basically expresses the tendency of an environment to receive or supply electrons. Whether in environment where different types of reactions, chemical reactions are going on, will accept or supply electrons can be indicated by using the redox potential, and redox potential basically is denoted by EH. So, EH is basically called the redox potential. Remember, in an oxic environment, the high redox potential, oxic environment has a high redox potential because oxygen is available as an electron acceptor. Obviously, in case of oxidized oxic environment, oxygen can accept the electrons. For example, iron oxidizes to rust in the presence of oxygen because the iron shares its electrons with the oxygen. So, you can see here, when 4 atoms of iron reacts with 6 atoms of oxygen. So, 4 Fe plus 3 O2 basically gives rise to rust or Fe2O3, ferric oxide. So, in contrast, an anoxic environment has a low redox potential because of the absence of oxygen. So, redox potential basically gives you an indication whether a particular environment is oxic environment or anoxic environment. In case of oxic environment, it has high redox potential. In case of anoxic environment, it has low redox potential because of the absence of oxygen. So, the more positive the potential, the greater is the species affinity for electrons and tendency to be reduced. So, in other words, the more positive the potential, that means more higher the redox potential, greater is the species affinity for electrons and tendency to be reduced. So, high redox potential means this environment is more has a more tendency to get reduced by accepting the electrons. Okay. Now, these tables basically shows the selected reduction half reaction pertinent to soil, natural water, plant and different microbial system. Now, what is half reaction? In case of redox reaction, the half reaction basically says either the reduction reaction or the oxidation reaction. So, any one of these reaction if you denote, then you will use this term half reaction. So, here basically we are using the reduction half reaction to see what are the major reduction half reaction which are pertinent to soil, natural water, plant and microbial system. We will be discussing some of them in details while we discuss the submerged soil. Just for some examples, you can see here the nitrogen dioxide, when it accepts electrons, it produces the nitrogen gas. When the nitric oxide accepts electron, it produces the nitrous oxides. So, first nitrous oxide converted to nitrogen, then nitric oxide convert to nitrous oxides, then nitrogen dioxides converted to nitrous, then the nitrogen dioxide can be converted to nitrous oxide. So, you can see how different species of nitrogen are changing their form by accepting the electron or by getting reduced. So, here one example is given for nitrous oxide to conversion to nitrogen, One is from nitric oxide to nitrous oxide, then nitrogen dioxide to nitrous oxide, nitrate to elemental nitrogen, then nitrogen dioxide to nitric oxide, then nitrate to nitrous oxide, nitrate to ammonium, nitrate to nitrogen dioxide, nitrate to NH2OH, and then nitrate to NH4 ions. So, you can see that by accepting electrons, the species of nitrogen or oxidized species of nitrogen can be converted into reduced form of nitrogen. In case of oxygen, you can see here this ozone, when it is accept electron converted to oxygen, then hydroxyl convert to this OH group basically converts to hydroxyl ion, the O2 minus converts to H2O2 or hydrogen peroxide, H2O2 can be converted to H2 or water, then oxygen can be converted to water, reduced to water, oxygen can be also reduced to H2O2, and oxygen molecule can be reduced to O2 minus. So, this is how you can see the oxygen species movement also in the you by accepting the electrons, and also corresponding PE values. We will be discussing PE values, and also equilibrium constants are given side by side. In case of sulfur, sulfur also undergoes different different oxidation reaction. You can see sulphate will be reduced to H2S or hydrogen sulphide, and it can also reduce to sulfur dioxides. So, you can see here the conversion of the sulfur species. Iron and manganese compound, you can see Mn3O4 can be converted to Mn2 plus, Mn2O3 can be converted to Mn2 plus, and also different iron compounds also, oxidized iron forms also can be converted to reduced compound by accepting the electrons. So, these are some examples of selected reduction half reactions which are pertinent to soil, water, plant and microbial systems. And also different Fe3 to Fe2 phenanthrolene, Fe3 to Fe2 plus, Fe3 to acetate, Fe3 to Fe2 malonate. So, you can see different species of iron can be formed by reducing the oxidized form of iron, that is Fe3 plus. So, similar for carbon also, from pollutants or other nutrient group also, analytical couples also, you can see the conversion of their oxidized form to reduced forms. Now, redox reaction of soil oxidants can be defined conventionally by the general half cell half reduction reaction, which is basically denoted by oxidized form plus MH plus Ne minus equal to reduced form. So, you can see here in this OX is the oxidized component or the electron acceptor, red is the reduced component or electron donor, M is the number of hydrogen ion participating in the reaction, and N is the number of electron involved in the reaction. Okay. So, the reduction half reaction for any redox reaction can be expressed in terms of this equation 1. So, the electrons in equation 1 must be supplied by an accompanying oxidation half reaction. Remember, we have talked about that oxidized species and the reduced species should coexist. So, the electrons which are basically accepted by the oxidized species to get reduced should be donated by accompanying oxidation half reaction. Now, to describe the redox reaction, an oxidation reaction must balance the reduction reaction. So, it is a complete, it is not a individual reduction half reaction, it should also involve the oxidation reaction to complete the total redox reaction. So, let us see. So, let us illustrate this concept for redox reaction of FeOH3 reduction, and let us see this ferric hydroxide plus 12 H plus. So, here M is 12, N is 4, ultimately we are getting reduced form of iron Fe2 plus and or in other words ferrous and 12 molecules of water. So, it is basically a reduction if we follow the equation 1, and also as we have talked about, thus there will be a coexisting oxidation half reaction also. You can see this CH2O, which is basically denoting a soil organic matter, will be reacting with water to form the carbon dioxide, 4 protons and 4 electrons. So, basically it is getting rid of electrons. So, this organic matter is getting rid of electrons, ultimately oxidized. So, this is an oxidation reaction, and so finally, if we combine these two reaction, oxidation reaction and redox reaction together, that is reaction 2 plus reaction 3, will get this final reaction where 4 molecules of ferric hydroxide and organic matter in the presence of 8 protons will produce 4 molecule 4 Fe ferrous ions, carbon dioxide and 11 molecules of water. So, this is the net reaction. Here you can see one thing, here the FeOH3 is getting reduced to Fe2 plus, whereas this organic matter is getting oxidized to carbon dioxide. So, it also supports our previous slide that the reductant will be oxidized and oxidant will be reduced. So, equation 2 basically represents the reduction half reaction, and equation 3 we have already talked about this half oxidation half reaction. So, the reduction reaction half reaction, that is equation 2 reaction, can also be described by calculating the delta G, which is known as the delta Gr, which is Gibbs free energy for the reaction. So, the Gibbs free energy for the reaction can be expressed in terms of this delta G0 plus RT ln natural logarithm of reduced by OX, that is oxidized, and H plus m. So, basically H plus to the power m, where G delta G0 is the standard free energy change of the reaction. So, from this equation we can have the Nernst equation, which is very important equation. So, this Nernst equation can be employed to express the reduction reaction in terms of electrochemical energy or in terms of millivolts. So, to express the reduction reaction in terms of electrochemical energy, we generally use the Nernst equation, and using the expression of delta Gr equal to NFE, such that we will get this value of EH equal to E0 minus RT by NF ln reduced by oxidized plus this expression. So, let us see what are the meaning of these expressions and these. So, again this is a Nernst equation. This Nernst equation says this EH is the electrode potential, or in the case of reduction half reaction in equation 2. So, this is an EH, this is basically a reduction potential. E0 is basically the standard half reaction reduction potential, and then F, which we are using here, is basically the Faraday constant. N is the number of electrons, we know that N is the number of electrons exchange in the half cell reaction. M is the number of protons exchange. So, M is the number of protons exchange, we know that, and the activities of the oxidized and reduced species are in parenthesis. So, oxidation potentials are more often, remember that these oxidation potentials are more often used in chemistry, while the soil chemistry, in case of soil chemistry, reduction potentials are more frequently used to describe soil and other natural systems. So, again these oxidation potentials are more often used in chemistry, while in soil chemistry reduction potentials are more widely used. So, again this Nernst equation basically comes when we express the reduction equation in terms of electrochemical energy in terms of millivolts, we can get this Nernst equation form. So, the Nernst equation is valid for predicting the activity of oxidized and reduced species only if the system is at equilibrium, which is seldom found in case of soil and sediment. So, this is one of the drawback of Nernst equation. Nernst equation can be valid only at the equilibrium, which is basically very hard to get in case of very heterogeneous system like soil. We have discussed that in details also. Now, what is the relationship between EH and pH? Okay. Now, using the values of in the Nernst equation, if we use the value of these R, that is the molar gas constant, that is 8.31 joule per Kelvin per mole, and then for Faraday constant we use a 9.65 into 10 to the power 4, it should be 10 to the power 4 integrate per mole, and then 298 Kelvin for T, and the relationship basically ln x equal to, we know that the ln x equal to basically 2.303 log of x. Then equation 6, that Nernst equation basically converts to this simplified form. Okay. Now, from this equation 6 and 7 we can see that as EH increases, so if EH increases, so if this term increases, so activity of the oxidized species increases and the H plus activity increases and pH decreases. Obviously, as the EH increases, pH will decrease. Okay. And as the EH increases, activity of the oxidized species will increase to getting reduced. Okay. Now, as EH decreases, obviously the vice versa, that means increases in the activity of the reduced species. So, if the ratio of the protons to electrons is 1, so here the ratio of protons to electrons m by n equal to 1, EH would change by 59 millivolt for every unit change in pH. So, if we consider this fraction equal to 1, then pH EH would change by 59 millivolt per unit change in pH. So, this is the relationship. Basically, there is a inverse relationship between EH and pH. As EH increases, pH decreases; as EH decreases, pH increases. Now, this relationship assumes that redox controls the pH of the system, and this assumption is valid for solutions only. But in soils, pH buffering is affected by soil components such as silicates, carbonates and oxides, which are not involved in the redox reactions. Thus, it may be inappropriate to apply the 59 millivolt factor in case of soil. Now, remember the thumb rule for using the redox potential in case of soil. EH is positive and high. When the EH is positive and high, then we use then it is a strongly oxidizing system. When the EH is negative and low, then it is basically a strongly negative reducing system. In case of submerged soil, which is basically a strongly reducing system, you will see the EH is basically negative. And when we convert a soil from oxidized to reduced condition, from aerobic to anaerobic condition, you will see the EH will move from its positive value to more and more negative value. So, EH, just like the pH, is basically an intensity factor. You know the difference between intensity factor and capacity factor. So, EH, just like pH, is an intensity factor, and the oxygen nitrogen range has been defined by and these different ranges of elements have been defined, or conversion of different oxidized form to reduced form has been accompanied by a range of EH values. For example, in case of oxygen and nitrogen, this range has been defined by a EH values of plus 250 millivolt to plus 100 millivolt. However, in case of iron, this range of EH changes from plus 100 to 0 millivolt. In case of sulphate, it varies from 0 to minus 200 millivolt. In case of methane hydrogen, it ranges from it range as less than 200 millivolt. So, in extreme whenever these millivolts are whenever this EH is very low, then you will see the formation of more and more reduced species than that of oxidized species. Now, let us see the relationship between EH versus pH and PE versus pH diagrams. So, the pH range was basically was narrower in reduced soils, and because it is having the negative EH. So, negative EH whatever you see is basically produced in reduced soil or submerged soils, then in oxidized soil, which is basically characterized by positive EH. So, again the oxidized soil is characterized by positive EH, the reduced soil is characterized by negative pH. So, the pH range was narrower in reduced soils than in oxidized soil. Based on these results, the scientist Busbecking et al. In 1960 divided the soil into three categories. One is normal soil, which is basically oxidized soil, wet soil, which is seasonally saturated, and waterlogged soil or submerged soil. So, here you can see the based on the pH and EH relationship, they have defined three different types of soil: waterlogged soils, wet soils, and normal soils. In case of normal soils, you can see the positive EH values. In case of wet soils, you can see there is a fluctuation of EH values. However, in case of waterlogged soil, the EH values are negative because they are reducing condition. They are residing in the reducing condition. So, this shows the one of the graphical representation of EH versus pH. Now, the reduction half reaction given in equation 1, remember the reaction with which we started this lecture, given in equation 1 can also be expressed in terms of an equilibrium constant K 0. This equilibrium constant K 0 can be defined in terms of redox versus oxidized, and then electron to the power n plus H plus a proton to the power m. Expressing in logarithmic form, we will get this form, and this in this equation this log minus log of electron concentration is known as Pe. In a similar way, pH is known as the negative logarithm of hydrogen ion concentration. So, P is basically negative logarithm of electron concentration, whereas pH is negative logarithm of hydrogen ion concentration. So, P basically an intensity factor, and it is an index of the electron free energy level per moles of electrons. So, in other words, it is the index of electron free energy level per mole of electrons. So, if we consider Pe in soil, in strongly oxidizing system, the electron activity is low and Pe is large and positive, since it is a negative logarithm of hydrogen and negative logarithm of electron concentration. However, in case of reducing system, Pe is small and negative. So, according to Sposito in 1989, he proposed that in case of oxidized soil, we know as oxic soils, they have a characteristic Pe value of greater than 7. In case of suboxic soils, the Pe ranges between plus 2 to plus 7, and in case of anoxic soil or reduced soil, the Pe varies from less than plus 2 at all the pH 7, at all pH 7. So, basically the ranges are consistent with redox control by oxygen, nitrogen, manganese iron and sulfur couples. However, the Pe range for most of the soil varies from minus 6 to 12. So, I hope guys you have learned something new in this lecture. We have defined first the reduction and oxidation and how these oxidized and reduced species basically coexist to govern this redox reaction. What is redox potential? How this what are the values of the redox potential in different conditions, and then we have talked about the EH pH relationship and then we have talked about the P. We have defined the P and how the P varies in soil. So, guys, let us wrap up this lecture. In the next lecture, we will be talking about more about P, and then we will be talking the other aspects of the redox reaction and redox chemistry of soils. Thank you very much. Let us meet in our next lecture.